So today I'm going to show you how giving a chemical formula like C9H8O4, you can identify its chemical structure based upon the different tests such as IR spectrum, mass spectroscopy, or NMR spectrum, and etc. and HNMR. So usually when you're given this type of question, first what you want to do, you want to find out the degrees of unsaturation. And how you're going to find the degrees of unsaturation? Using this specific equation. So what you're going to do is 2n positive 2 divided by negative minus x divided by 2, where n is number of carbon, okay, and x is number of hydrogen. And in this chemical equation, we're gonna omit or we're gonna ignore oxygen. So no matter how many oxygen you have, if you have 10 or 2, it doesn't gonna matter. So in this case, we're gonna substitute the numbers in. Instead of n, we're gonna put in 9, and instead of x, we're gonna put in 8. So let's see, using a specific calculator, our good friend, it's always healthy. So what you're gonna do is 9 positive 2 negative 8 divided by 2, it gives us 6. Okay, so we have a 6 degrees of unsaturation. So what does it mean? Essentially mean unsaturation is a measure of finding out how many double bonds we have inside our equation, inside our chemical formula. So if we have 6, it essentially means we have 6 double bonds, or if triple bonds counts as 2. But usually in this type of reaction, I don't think the professor would want to trick you. If you have this high number of degrees of unsaturation, what it means essentially means you are dealing with the aromatic ring. So aromatic ring itself is gonna take up 4. So it's 1, 2, and 3, and whole ring count as 4. So we have 2 left. Let's find out. Let's use a different test and find out if we can find more things. So keep in mind while you're doing this substitution, always consider this reaction. You don't have a nitrogen, so for example, here in the IR spectroscopy, you'll usually be given this type of tables. Okay, it's usually this type of tables where you're usually given like names. Here, when we have this type of bird, it usually indicates of OH. Okay, this we have a broad peak. This is OH. So we have 1 OH. We have 2 more fragments. So let's see, using this, where would our 2 fit in? Okay, where, if you can see, it's not going to fit in amide. We don't have nitrogen anyway. We're not going to fit in, for example, in the ketones. If you can see, if in the ketones, it is not going to fit in, okay? Because here it is 1766 and 1685. So instead, if you can see, if you have OH here, for example, we're going to have a carboxylic acid. And the carboxylic acid is a sensible assumption. It's in between 1700 and 1725. Okay, so we're gonna say maybe here, maybe CO carboxylic acids, maybe, or finding out more, we may have ester group as well. We may have ester present, so maybe ester. Why not? So we have ester. Maybe 2. I mean, that makes sense, because here's the deal. If ketone would make sense as well, for example, for this band, but keep in mind that we have a 4 oxygen and we're only left with 2 double bond. So we're gonna make sure that we're gonna fit those 4 oxygen with the type of functional group that has only 1 double bond. So that 1 and 1 each would give us 6 double bond as whole. And we're still gonna satisfy the criteria that we have a 4 oxygen. We may have a ketones, but we're gonna find out in the next test. That's what it's gonna really tell us. So next of all, we're gonna use this UV spectrum. It usually wouldn't give us accurate results, but you usually would do it. So it would be 10.4.1. So it usually have given this E. So we have a log 10 to E to power of 4.1. We have to do reverse log to find out number of E. Okay, so this case it is 201258-9E. I forgot what the E stands for, but I think that's some measurement for the UV spectrum. So then the next one would be 1000. Okay, so we have 1000 E and 12,500. So then you're gonna rotate, use your table which will be given. If you ask to do UV spectrum, you're not gonna ask if you're in like a high school level or college level. In uni, you'll be given something like that. So here, for example, you can see acetone is kind of matching the criteria, doesn't 100%. Okay, so we have, for example, 1216, which is close to that, and we have a 1600, which is fairly close, not 100%. So it is giving us this acetone, which is the structure as you can see here. So maybe, okay, then we could have one carbon here, one double bond. Okay, I mean, so this is assuming that we have a ketone. Okay, so this is ketone, and ketone is different in compared to acid, so we have to expect some differences. But here you're not gonna really understand the structure of using this, so we have to hop into the mass spectroscopy, which I usually do it at the end. It gives me a better understanding, and I'm going to do it at the end in this video as well. I usually wouldn't get help from this at all. I mean, these two would tell me all I need. So for example, looking at the carbon NMR, we have one peak which is CH3. Why is it CH3 you want it? And it's just downfield. Okay, it's downfield. It means it's not usually close to the oxygen or any negative electronegative atoms. So you should be having this. Okay, so here what is it telling you is that it tells you CH3, as you can see, would pick up. So it means we have one CH3. This is solvent, we're not going to care about that. Then we always come at the end. This is a very important case because it tells you whether we have we do have something ketone or acids. And in this case, let me bring my table. What is it telling you? Well, or you recall, what is it telling you? So it is telling you for ketones you must have 185 to 225 ppm shift to get it. But do we really get that peak? No, we don't have it. What we have is between 170 and 170 to 180. So 170 to 180, where does it fall? It falls in acid. So this confirms that we are dealing with the 2CO, because we have two peaks, that we are dealing with the carboxylic acids and then ester. Okay, so this is a confirmer. Then we have 4 more peaks. So if you have 2 peaks, it means we have a hydrogen. If we don't have a peak on above, it means we are just single carbon. And assuming with the aromatic, it makes sense because if you have you're gonna have a symmetry here. So this means we must have a para substituted atom. So why I'm saying para? Because para is usually the one like that. Okay, X here and Y here. It means we are dealing with the symmetry. These and this and this and this are similar, and that's what we really get here. So we have two CH aromatic. Okay, so here recall CH and CH3 both point out we can't have a CH3 in aromatic ring. Okay, it doesn't make sense. So we have a 2 here, which means this one and this one are symmetry. That's why we're getting 2 picks up of CH. Okay, which makes sense. Then we also have a 2 here. Okay, 2 here, which makes it is from this one and this one. Okay, so we have 2 C aromatics as well. 2 car C aromatic, 2 carbon aromatics. Okay, cool. So we have what? We found out carboxylic and esters are the functional group. We found out 2 CH of the aromatic. We have 1 C aromatic, and we have 1 CH3, which is in downfield located. Now, let's do the most important part, which is HNMR. I'm running out of time, so maybe speed it up. So we are given with D2O. What does D2O means? It's signifying of OH group. So if we have kind of picked like that at high end, which is 11, this is an OH. So this would be really tell out that we are dealing with the carboxylic acid. So we must definitely dealing with the carboxylic acid. Okay. So here the idea here is just you want to add up to 8 hydrogens. So here we found 1, so we now be dealing with 7 hydrogen only. We know that in the what's it called, in the aromatic, so we are dealing with 4. Okay, so we are dealing with 4 hydrogens. So this means this must be 2 hydrogens and this must be 2 hydrogens. So this give you 1, 2, 3, and 4. 4, 4, 5. 5. What is 8? 8 negative 8 subtracted by 4. What would give you? 3, wouldn't it? So 3H. So this would be our CH3. In the hard case scenarios, what you can do is just you're gonna measure each base pairs and you're gonna compare with them and find a ratio and get a hydrogen. But in this easy type of question, you don't really have to do it. Okay. So yeah. So then we have that too. Again, if we always find this type of the similar length, okay, these are real similar length of aromatic ring. I think it's about I have to pause and make a measurement and I'll tell you soon. So I found my ruler, so that would be 1.5. Okay, 1.5 again, 2.2. So they say 1.5, 1.5, which is similar. This again tells you we are dealing with the aromatic ring that is para-substituted. That is symmetry. We have these two being symmetry, and that's why we're dealing with that. So this now, let's do a bit of recap. See if we can actually figure it out. Pause at this and see if you can actually figure it out at this moment. And if you can, that's very good, I hope. So what do we, so far we have done what? We know it's para-substituted. We know we have 1 carboxylic acid and 1 ester. So if that is the case, how many configuration can we have? I mean, if you have a carboxylic acid at one end, which would give you like something like that, how would the ester look like? Okay, it will look something like that, wouldn't it? This is really small, but I'm gonna make it so O. We always ester, recall. O here, CH3. Okay, this is our end structure. So let me draw it better here. Okay. So 1 carboxylic acid, right? Okay. And we have 1 ester left. Okay, so this was our ester, carboxylic acid. See, I didn't even look at the mass spectroscopy. I just found it out. It's that easy. You don't even need to look at the mass spectroscopy. And yeah, so, but if you want to have a look, it's just you have to subtract this by this. For example, I'm just going to go through this one. For example, you subtract 180 minus 138. So what would happen is that you have 42 base pairs. So you have 42 base pairs. So you have to find out what fragments out of this would give you 42. So for example, if you found, you can, for example, say 12 plus 12, which is 2 carbon, positive 2, giving you 2 hydrogen. Okay, positive 16. It gives you 14. So 42. So what it means is that if we have something like that, we must have it something like that. But do we have it something like that? Well, we had something here, recall, from the carboxylic acid part. Yeah. So you can easily find it here like that. Ben, I hope it was helpful.